good afternoon. We'll get started. So today, the main goal of the day is to talk about Primaldual interior point methods. So before we get into any details, essentially, what we are going to do today is, so last week, I guess that was on Monday, we spoke about the barrier method. Okay, the barrier method is in some way the most basic type of interior point method. If you recall, the key ingredient of the barrier method was to essentially replace a certain set of inequality constraints with a barrier function. Now, the barrier method is a fine algorithm, but it's really not the most effective or the fastest way of solving convex optimization problems via interior point methods. The fastest way of solving, both theoretically and practically, the fastest way of solving convex optimization problems with interior point methods is with the class of methods that we will talk about today, Primal-dual interior point methods. In some way, it's just a little variant. It's a variation of the barrier method that we discussed a week ago. So a lot of what we are going to see is familiar because we have already seen the main ideas. But there are certain details about the specific, if you want, implementation of the algorithm that are a bit different. And it turns out that those differences actually have important implications on how the algorithm performs. In the homework that you're working on, hopefully you will get to appreciate the difference between, again, the barrier method and a Primaldual interior point method. So let me recall something that we are going to use today. So last time we revisited duality. And so here's our generic form of a convex optimization problem. So here we have a convex objective and we have some convex inequality constraints. We have the Lagrangian function, the primal problem can be written this way, min max. Then the dual problem is what we get if we flip maximization and minimization. So let me keep it here, the dual problem. And then a couple of important things, the optimality conditions. If we have, say, a nice enough problem, if our functions that define the objective and the nonlinear constraints are convex differentiable, and if we have strong duality, for example, if we have some kind of Slater condition that ensures strong duality, then the KKT conditions are both necessary and sufficient for the primal and dual solutions. So what that means is that to find this solution to the primal problem, the optimal x for the primal problem, the optimal UV for the dual problem, that's equivalent to solving that complicated system of equations there. Okay, so we have essentially the constraints, right? This is complementarity. Remember this notation, big U is the diagonal of U. Nabla H is just the matrix that has as columns the gradients of the H functions. And then we have the three conditions there. So that's the optimality conditions for the original problem. And then we have the central path equations. And let me, for a moment, compare these two, because this is in some way at the heart of interior point methods, both the barrier method and Primal-dual methods that we're talking about today. So we have the central path equations, which we obtained by looking at the optimality conditions for the barrier problem. Right? So as you can see there, the idea is to replace the inequality constraints with that barrier term. And we put a weight in front of it, tau. I'm going to use tau today. Think about tau as 1 over t, if you think about what we did a week ago. And the optimality conditions for this problem turn out to be like this. Okay, so we have the first equation is identical to the first equation for the original problem. The second equation is maybe the key difference. The second block of equations here, instead of complementarity, we have this kind of tweaked complementarity. So component-wise, the H and the U's have to multiply to tau. Then we have feasibility, AX equal to B. And we have strict feasibility both for primal inequality constraints and for the dual derivative. Okay, so those are the optimality conditions for the barrier problem. The collection of the solutions to this system of equations for all tau, that's what we call the central path. And then if you have a point on the central path, that is a solution here, we have this nice duality gap. And this is something that we did last time. If you look at the difference between the primal objective function and the dual objective function, then the size of that gap is m times tau. Okay. So that's a quick recap of what we've been doing in the last week. So today, here's where we are headed. We will talk about Primaldual empirical method. I will describe the algorithm, and that is really the first item. Is really the main point of the class today. Okay, so that is really the important part. Then, just to add a little more to that, we look in a little bit more detail, the special case of linear programming, and then if we have time, we'll get to semi-definite programming. So there was a couple of slides that I did not cover last class on semi-definite programming. I'll get to those at the end of class today, if we make it that far, the semi-definite programming. I'm being optimistic that I'll make it that far today. So let's go over that. So here, let me put back the equations that characterize the central path, okay, the optimality conditions for the barrier problem. Here is, if you were to compare the barrier method, that's what we discussed a week ago, versus Primal-dual methods, that's what we are going to do now. There are essentially a few differences between the barrier method and the Primal-dual method. If you think about the barrier method, in principle, the barrier method was worked the following way. You picked some weight on you picked a barrier problem, so you picked some particular value of tau, or if you want, t. And then you solve that problem. Okay? Or you solve it with sufficient degree of accuracy. Then you change the value of tau, and then you use the previous iterate as a warm start for the next barrier problem. And you'll keep going with that as you approach the solution to the problem. So if you think about the barrier problem there, when tau tends to 0, that approximates the solution to the regional problem. That's what the barrier method is. So in principle, each time you pick one of those barrier problems, you're going to apply Newton's method to solve it sufficiently accurately. By contrast, Primal-dual methods, they're not going to, each main iteration of Primal-dual methods is only going to use one Newton step. One Newton step. Primal-dual methods are not necessarily going to be feasible, meaning that we will not necessarily satisfy any of these constraints. The only constraints that the method is going to satisfy at each iteration, the only constraints that we will enforce for sure, are these constraints. But we are not going to enforce any of the other constraints. In principle, when you are dealing with a barrier method, at the very least, some of those constraints are satisfied. And then, as I already mentioned, Primal-dual empirical methods are typically more efficient, both in terms of what the theory says about them, as well as what the computational experience suggests about how they work. Something that we are actually not going to see in full detail because it gets a little bit too technical, but essentially you have some nice theory that ensures that if you have a nice problem with Slater condition and the necessary, say, regularity conditions, then the Primal-dual empirical method achieves a little bit better than linear rate of convergence. So let me go ahead and describe the algorithm, the Primal-dual algorithm. So here, let's see, let me play with this again. So here, you see the description of the Primal-dual method. So here is, once again, the equations that you see right there. Maybe if I take this away. The equations that you see there are just the same as the equations that we saw a moment ago. So those are the central path equations, right? It's exactly the same equations I have here. I just moved everything to the left, just because that's going to be a little bit more convenient to describe the algorithm. Okay, but the central path equations there are just identical to the equations we had here. Those are the optimality conditions for the barrier problem. So now, the key observation, or the key idea of Primaldual method is that, like the barrier method, the main, if you want, the main hammer that we use, the main subroutine that we use to make progress in the algorithm is Newton's method. But unlike the barrier method, where you can think about the barrier method as using Newton's method for a linearly constrained problem, here it turns out to be more direct or more appropriate to think about Newton's method as a method for root finding. So think about the first three equations as a nonlinear system of equations. And our goal is to solve that system of equations. So if you do a little quick count, tau is a parameter that is fixed, right? So you have the x variables, right? The m dual variables u, right? And let's say that the equality constraints are p, so you have p variables v. Now the first block of constraints there is of size n. Okay. The next block is of size m, as many as constraints you have. And the last block is again of size p. So you have a square system of equations that you have as many variables as you have, as many equations as you have variables. So it's a perfectly well-suited problem to be tackled via the root finding Newton's method. So what does the root finding Newton's method do? Well, what we do is we iterate in the same way that we had previously discussed. So let me recall this real quick. And let me recall this with if we have, say, I'm going to use the following notation to make it consistent with what I have there. Let's say that R is a function from, let's say, RD to RD. Okay, so the Newton's method for the root finding, for solving R of W equal to 0, right? Does the following. W plus is W, and then we subtract the Jacobian here. So this is, we call it R prime of W times R of W. Okay. So think about our R as this guy. This is our R. Okay, these are the equations that we want to solve. This guy here is the Jacobian of R. So if you go through the drill of computing the derivatives of each one of these functions, you see that when you compute the derivatives of the gradient, then you get the Hessian. When you compute the derivatives of all these terms here with respect to x, you get the Hessian of all the hi. That's the first term here. And then the second block here are the derivatives with respect to u. So the derivatives with respect to u are very easy here, because this is linear, so that you get that block. And then the third block are the derivatives with respect to v. And again, that's very easy because this is linear. So the derivatives with respect to v is the matrix A transpose. And then you can do the same exercise in the other two cases, and you get the other derivatives here and here. Okay, so in particular, this last one, you only have the block of derivatives with respect to x, so the other vanish. So there's a lot of terms there, but at the end, it's a very simple idea. All we are doing there is computing this Newton step. Okay. So I have to admit, the first few times that I was learning this subject, I sometimes got a little confused just because I didn't, somehow I was not maybe, I was missing the big picture when I was trying to look at all the details here. But the details not as important as the main idea is just that you're applying Newton's method for root finding, for a root finding of this function R, where R is the collection of the optimality conditions. Okay? And maybe a little piece of notation here, this big block in the middle, big H, is just shorthand for diagonal of H of X. So that's an n by n matrix that has on the diagonal the HI components. So now, if you think about it for a moment, this would be pure Newton's method, right? This would be pure Newton's method. So obviously, we are not going to do pure Newton's method. We are going to do Newton's method with some appropriate step length. So this will compute as what would otherwise be the pure Newton direction. But we will not necessarily take the Newton direction. We take, so we do some line search to take a certain step length on the Newton direction. So this is probably the main, say, technical slide that I'll present, that I'll flash today. Maybe I want to pause here for just a few seconds in case there's a question about this. The algorithm is essentially based on playing with the solution to that system. All right, so let me keep, since that's so important, let me keep that system of equations here. So that we will call, this guy is typically called the Newton system. This guy, this we call the Newton system. That system of equations. Okay. And again, R are the left-hand sides of the optimality conditions. So now there is some kind of terminology, and part of this I have to admit is was coined by some of this terminology was coined by people working on empirical methods, but the terminology of surrogate duality gap, the only person that I've heard use this, or the first person that I heard use this terminology was Boyd. And Boyd really made this subject very popular. So many other people picked up on that terminology. So yeah, we'll go with that. So little thing about the residual here. So the system of equations that we want to solve. This is called R because it is often the case that we think about each of them there as a residual. So in particular, the first block of equations here, the first component of R, that you can think about that as some kind of dual feasibility equations. It turns out that the first block of equations there, that's exactly the same first of equations that you would see, for example, in the dual of the primal linear programming problem. In general, that first block of equations essentially is a duality constraint that you want to satisfy. So, so that's often called R dual, the dual residual. The last block here is called R primal, the primal residual, and it refers to the residual of the primal equality constraints. So these constraints, so that's the primal residual, and then the middle block, the one that is here, this middle block, that's the centering residual. So how do the equations that are essentially the tweaked complementarity equations, how much are they evaluated? So those are the three blocks of residuals. It's just the three blocks that you see here. Now, why do we distinguish them? Why do we put R primal, R dual, and R center? Because let's recall something important about how the algorithm is going to work. These are going to be typically infeasible algorithms. So the algorithm is not really going to satisfy that the residuals are equal to 0 in the iterations, only as it converges. So what the algorithm is going to do is essentially aim to make all of those residuals 0 in the limit. So that's those are the residuals, and then this is called, if we have some x and u, and x makes all the h functions less than or equal to 0. and U is non-negative, then this product, H transpose U negative sign, this vector with a negative sign is non-negative. U is also non-negative, so that's going to be a non-negative number. That is called the surrogate duality gap. Okay? So it would be a duality gap if both the primal constraints hold and the dual constraints hold. So if we had both R primal and R dual equal to 0, then X would be a primal feasible point, and UV would be a dual feasible point, and that thing, H transpose U with negative sign, that would be the difference between f of x and the dual function. So if we had residuals equal to 0, this would be a genuine duality gap. Since typically we are not going to have the residuals equal to 0, it's not a duality gap, but it's kind of like a fake duality gap, so we call it a surrogate duality gap. Okay. One little observation that I would like to make here is, so this is a very simple observation, but it's kind of, I think it helps to understand the algorithm. So observe that for a point x, u, v to be on the central path, okay, for a triple x, u, v to be on the central path, that means that these equations are satisfied. These equations are satisfied. Now, if you think about those equations, what that means is that the residuals, right, all of them have to be equal to 0. The residuals have to be all equal to 0. Now, if the residuals are all equal to 0, then in particular, the block here, the middle block, this is that each ui, hi is equal to tau, right? So, negative, right? If you are on the central path, then the value of the surrogate dual is n tau. And it turns out that the reverse also holds. That is, you are on the central path if and only if, of course, these things are positive and the residual is equal to 0 for that value of tau. Okay, so the surrogate duality gap, on the one hand, it's like a fake duality gap, but it also sort of gives me an idea of if I were to judge how close I'm to the central path, this value of tau would be like the one point on the central path that I should be comparing myself to. So that's duality gap and residuals. Okay. Now let me keep again. Keep that guy there. So, actually it's here. Yes. So have that there. And now we are ready for the algorithm. Okay. So here is the algorithm. So here's how a Primaldual algorithm works. So we are going to make use of this little observation here. In fact, given any x and u, we will define tau of xu to be the surrogate dual divided, the surrogate duality gap divided by m. So that is that will be the tau associated with x and u. And again, the rationale for this is that if the x and u that we begin with are indeed on the central path, then that will be the tau for that pair of data. So the algorithm works as follows. We choose an initial point, x0, u0, v0. The only thing that that initial point has to satisfy is that the last two constraints hold exactly. So the only thing that we are going to require is that both of these constraints hold. So h and u are respectively strictly negative and strictly positive. Then we compute the Newton step. So the Newton step, I had it back here. We compute the Newton step, that is, we solve this system of equations. That gets us the Newton step at the current point. Okay? So we We compute this at the current point, so the x here, u and v would be the current xk, uk, vk. And the tau that we pick, is not the tau defined by x and u, but that tau shrunk by some constant sigma. So, so that would be, we compute the Newton step. So this is as if we are chasing, this would be as if we are chasing the point on the central path corresponding to sigma times tau. Okay? So we are going to chase a point on the central path, but we are at the same time trying to drive tau to 0. Then this will compute us a Newton step. Okay? If we were going to apply a pure Newton's method, we would take exactly that step. But there are some complications with that. I will detail them in a moment. So instead, we choose a step length. The step length is going to be actually between 0 and 1. And then we move along that Newton direction. We move only, say, theta k. So after choosing a certain step length, theta k. Okay? So again, there are many indices and triples there and stuff, but at the end of the day, all we are doing there is aiming to solve this system of equations with Newton's method. We are using xk, uk, vk as the current point, and we are just aiming to move to a better solution for this with a certain value of tau. The value of tau actually is a little bit smaller than the tau corresponding to the current point. So, so this is very greedy in some way. We are aiming to solve this, but we are also aiming to, at the same time, shrink tau towards 0. So a little polygon notation to what we discussed last week. It was just a little bit easier to not to have too many fractions, to phrase things in terms of tau and sigma. But tau and sigma correspond exactly to what we called last week 1 over t and 1 over mu. Okay. So that is the algorithm. Okay, that is the algorithm. That essentially is the central part, the main part of today's class. Maybe one important detail that is, of course, not explained here is, so you see how we compute, you know how we compute the deltas, right? That's solving the Newton system of equations, which is here, the Newton system. And you also know how to compute tau. Tau is at the top there, is in terms of the surrogate royalty gap. The one thing that is still pending, and I'll explain in a moment, is how we choose theta, how we choose the step length. Because essentially this is, if we were to choose a pure Newton's method, it may not have global convergence. So how do we choose theta? Let me explain that now. Okay. So let me keep, let's see, so this is
Excuse
9.
me.
Yes, please.
Why do we shrink the tau here?
Yeah, so let me put back maybe something here from the very beginning, right? So actually, these are the central path equations, right? But remember, our ultimate goal, the central path equations are, how should I put it, nice, pretty, but that's not the main goal, right? Now, our goal is to solve the original problem. So our goal is to solve this guy. So the tau is essentially, the central path is like a means to an end, right? Our goal is to solve that for tau very small. Ideally, our goal is to solve that for tau in the limit 0. So that's why the algorithm is shrinking tau, because we want tau to go to 0. Okay, and the way that we do it is we take some value of sigma. I guess very standard values to take are like 1 over 10 or 1 over 5. And then, again, each Newton step is aiming to the solution of the new point on the central path for a smaller value of tau. All right, so let me explain here. Let me keep the algorithm here. Okay, this is the algorithm. And let's see. Yeah, so this is the algorithm. And let me explain how we choose. So this is a key step. How do we choose the step length there? How do we choose theta? How much we move along the Newton direction? How do we choose theta? So we want to choose theta so that we update the points that way. There are two important things about how we choose theta. First of all, the algorithm, the one thing that the algorithm has to maintain throughout all the iterations, the one thing that we always maintain throughout all the iterations is that h of x should be negative and u should be positive. So we always maintain that. And then the second goal of the line search is that we want to make progress on our residual. We want to get closer to solving the central path equation. So we want the norm of the residual to go down. So the way that one way to achieve both of these, and this is very much the way that essentially all implementations of empirical methods work. There are some variations, but the main idea is that, well, first of all, we choose, we do this in some kind of multi-stage fashion, right? So we need to ensure the inequalities. The one that is most straightforward is to ensure the inequality for u, because that only requires checking that whatever the delta u is negative, that we don't take a step too large in that direction. So we choose theta max to be the minimum of all those numbers. So this ensures that if we take any step length up to theta max, the new u will still be non-negative. Okay? So that would be theta max. And it also ensures that the step is bounded by 1. And then, to ensure the other two, we do some kind of standard backtracking. So we start with almost theta max. We start a little bit less than theta max. And then, as long as we haven't ensured that this guy is negative, we shrink it by some factor, say, beta. And we stop when finally we make all the hi's negative. And then we ensure that there is a sufficient decrease in our residual relative to the step that we are taking. So that is, we keep again shrinking the step length until the reduction in the norm of the residual is at least alpha times theta times the previous norm of the residual. So these two will ensure that at every step we will maintain the above two goals. That is, that we maintain feasibility, strict feasibility, but not, maybe I should backtrack. We maintain h of x negative and u positive. Okay? So we maintain the strict inequalities, and we reduce the size of the residuals. So I have a quick question for you. To throw out a little pop quiz question. Why do we choose something like this? Why not start with theta equal to theta max? What's wrong if we start with theta equal to theta max? So the theta max here, right? Let's ignore this for a moment. Suppose that the theta max is the mean of all those values. So that means you looked at the delta of u, that is in some way the biggest relative to u in absolute value. Right? So if you move exactly that size, what happens to that component of u? It goes exactly to 0, right? But the empirical method actually needs to have everything strictly positive. So the empirical method, because of, if I go back a couple of slides, because of how the algorithm works, right? The Newton's, everything here, we want u to be positive. Throughout, we want u and h to be positive. So in that one, in this one step here, we don't go all the way to theta max because that would make some of the components of U, at least one of the components of U 0. We want them all to be positive. It turns out that actually the way that the line search works can be extremely aggressive. We can go 99% of the way before we hit 0. So we can go very far. We still maintain things positive, but we are very aggressive on the step length that we take. So that's that. Now another pop quiz question for you to think about. Why do we want to pick 1 here? What's so special about 1? Why don't we start backtracking with 10 or 0.1? Why 1? What's so special about 1? What is so special about 1 in terms of, say, Newton's method? So the pure Newton's method takes step length 1, right? And what is special about that is that if you can take pure Newton steps, eventually you get quadratic convergence. So if you can, all other things satisfied, it's always the Newton's method. The ideal step length is 1. Again, because that's connected to a very special property of Newton's method. So that's why the backtracking here begins at 1, as opposed to a possibly larger value. Okay. So that essentially, those are the main details of the Primaldual interior point algorithm. Okay. There are a few other bells and whistles, but those are the main details. Yes?
In the second condition, you want to update theta by beta times theta. How do you ensure that inequality eventually holds when you keep updating theta?
Yes, so let's see. To ensure that this inequality will hold, this one is that's an easy one because we start with, this is key, these two conditions. The first condition, h of x negative and u positive, they are maintained at every iterate, right? So if I am at iterate k, h of xk is negative and uk is positive. So if the step length is sufficiently small, since these are nice differentiable functions, they're continuous functions, if the step length is sufficiently small, I will not violate that inequality. Okay, so this will eventually hold. This will eventually hold just because of continuity, because the h at x is negative. So if the step length is sufficiently small, that will hold.
In the second condition.
Okay, the second condition, good point. The second condition will hold because you have, this has to do with, this is a little bit more technical, but that essentially has to do with the fact that you're using Newton's method. Okay, so you're using Newton's method here. So there is, I guess if you think about the norm, okay? If you think about the norm of, see, I haven't thought about this for a moment, so it will take me a moment. Essentially, you want to claim, this is the claim. This is a very good point, and I realize it's something I didn't think of beforehand, so let me see if I can think on my feet. The claim is that if you look at this function, okay? If you look at that function, let's say that this is f of w, then this delta w, so this is delta w equal to negative r prime w, rw is a descent direction for f of w. Okay, so I actually did not do this beforehand, but I'm pretty sure that happens. The Newton step is a descent direction for the norm. Okay, so if I move along that direction, eventually I will make this guy decrease if the step length is sufficiently small again. So this is essentially the same thing as when you do gradient descent. Okay. When you do gradient descent, there is a similar type of minimum decrease that you have to satisfy for doing your backtracking. How do you guarantee that eventually that condition holds? Because you're moving in a descent direction. So here, the Newton direction is a descent direction for the norm. So that also guarantees that that will hold.
But the descent direction only ensures that the first term is less than the norm of the original point. Not that norm times 1 minus alpha times theta.
Well, so let's see. You know what? Let me suggest something, because this is a very interesting question, and I need a moment to think about it on my feet. This is also an ideal moment to take a quick break. So let's take 5 minutes, and then that will allow me to answer it, because this is a very good question. I want to give a better answer to that. Okay, so let's take 5 minutes, and I promise we'll settle this. If we don't settle it, then we have a nice question for a homework, right? Okay, that's always a good solution to that kind of problem. So let me pick up on this question, because this is a very good point, and it's something that I actually realized I didn't think before class. Essentially, I think the answer that I was giving you is correct. So first, this is not trivial, but I guess before everything, I was missing an inverse here. So, okay, so this, of course, has to be Newton's method is R prime W inverse R of W. So this is a little quick observation. If you look at delta W to be the Newton step, that is a descent direction for this function. Okay, you could actually take f of W, the norm of R also. It would be a descent direction for the norm of R. Okay, so this is also, I guess I should write that down too. Delta W is also a descent direction for norm of R of W. Okay. So the norm will decrease if you move along that direction. It's a direction of decrease. Now, what that means, and I think your question, what that means is that eventually I could make this guy be less than or equal to the current R minus alpha times theta, right? Minus alpha times theta. Now here's the deal. The reason that I can make this decrease be relative is because the R's are monotonely decreasing. So there is the fact that I can make the decrease be absolute implies that I can also make it be relative, because the size of the residuals is decreasing monotonically. So there is no, how should I put it? There is no fishy business here between. I could have written this in terms of just an absolute decrease, but it's more convenient, it's more conventional, it's standard to write it in terms of relative decrease. Okay, but there is no. It will eventually happen. The question that is a lot harder to answer, and I will not answer it because it requires too many technicalities, is you could say, okay, fine, these two conditions will eventually hold. But what if you jam, if somehow the step lengths get so tiny that the algorithm barely makes any progress? That is very hard to prove, but it can be done. It can be proven that, in fact, the step lengths are bounded away from 0 so that the algorithm actually doesn't jam, it makes progress. Okay? And that requires a lot of complicated calculations that we're not going to get into. I mean, they're not complicated, but they're tedious calculations that I'm going to omit. So that is a much more delicate question to ensure that these two conditions are eventually satisfied for a decent size step length. So take my word for it, they are, and the algorithm does work well. So that was the main thing that I wanted to get through today. Again, the Primaldual interior point algorithm. So there you have it. There you have it. There was this guy, I remember when I was finishing grad school, interior point methods were still a very active area of research. And then there was this professor from Rice University that gave a talk on interior point methods, and he flashed a little MATLAB code that had like 10 lines of code. That was it, 10 lines. Essentially, these lines and a few other lines of just the detailed linear algebra calculations. And with 10 lines of code, that code can solve essentially any linear program of some kind of moderate size. So it's really a remarkable class of algorithms. So let me actually look at the linear programming case in some more detail, because the linear programming case is a little bit simpler. We don't have the equations, as you will see in a moment, get a little bit simplified, and it allows us then to look at some additional issues that are just a little bit easier to see in this context. So let's look at linear programming in particular. So let me keep it here. So here's linear programming, and I am using this notation on purpose, not to torture you, but to because this is very, very common. Instead of using U and V, as Ryan has been doing, as you see in Boyd and Vandenberg's book, it's much more common to use Y and S for the dual variables. So the dual usually is written this way. So think about S as U and Y as V. So when you go through the Lagrangian and everything, you get that the dual is here. And there is some kind of cool history about linear programming and the various classes of algorithms for linear programming. So let me indulge myself in sharing some of this history with you, because I think that this is kind of one of those cool things about learning the subject, that we are fortunate enough that the history of optimization has occurred. Good part of the history has actually occurred over the last century. So it's like we have seen history develop. So Danzig was essentially the creator of this linear programming and the simplex method, which is remarkably still one of the most powerful, most popular algorithms used now. Many large-scale industrial organizations rely on the simplex algorithm to do all sorts of various kinds of operations. There is a very interesting analogical example that was cooked up by Klee and Minty in the 70s of a linear program with n variables and 2 n constraints. It's essentially a cube, and that cube has 2 to the n vertices, and the simplex method may need to visit all of them. So for many years, there was this important kind of theoretical question about if there was an algorithm for linear programming that was efficient, that would not have that kind of exponential, say, potential explosion. So Kashian, a Russian in the late 70s, published the first polynomial time algorithm for linear programming. There was a headline in the New York Times, because that was at the time of the Cold War. And then everyone in the US was freaking out that the Russians were ahead of us, and they had cracked this important mathematical problem. But the ellipsoid method, which is the method that Kashian developed for the first polynomial time algorithm, at least for a good number of years, didn't go beyond just being a theoretical result. It didn't really become a computational tool. So then Karmarkar, in the 80s, developed, I think this happened when he was either finishing grad school or soon after. He developed the first polynomial time empirical method. And this really created an explosion of research in optimization. So a few years later, Reininger gave a Newton-based empirical method algorithm. That algorithm turns out to be very similar to the barrier method, to the Primaldual empirical methods that we just discussed. And the last time that I spoke about something like this in a previous version of this class that Ryan invited me to, I ended this sentence here because I didn't know any better. But it turns out that this was, actually maybe I ended it here. Okay. But then I added this because this is very, very recent work. There are these 2 guys who were graduate students at MIT. I think they both graduated last year. We tried to hire Lee, but contrary to any kind of common sense, he chose to turn us down and go someplace else. That was unfortunate, right? Especially for him. Right? And he's a co-author at Stanford they have this very, very amazing result about an improvement on what was up until 2 years ago the best known theoretical algorithm for solving linear programming. So essentially the type of methods that we are discussing today, Primal-dual, interior methods, in theory, those are the most efficient ways of solving linear programming. And then these guys came up with this very clever variation on the ideas that we are discussing today that appears to improve the theoretical complexity. The paper is complicated, it's long, and it's one of those things that still has to go through the regular hurdles of publication. But it looks like it's a sound result. So, maybe 2 or 3 years down the road, we will be not talking about Primal-dual interior methods, but instead we will be talking about the Lee-Silford algorithm. Now, the modern state-of-the-art commercial solvers for solving linear programming, not only commercial, but also open source solvers. Many of them use both the simplex method and the empirical method. So if we think about the central path equations, okay, so let me put them back here. If we think about the central path equations for linear programming, okay, so these are our 2 problems. So the central path equations before had this form. In the linear programming case, it turns out that the central path equations now have this much more compact form, in part because the primal and dual constraints are nice and linear, so we have this form. The original problems can be written as above. So those are the central path equations, so let me keep them here. Yeah, keep them here, central path equations. And the Newton system, which is, remember, linearize this. The Newton system comes from thinking about this as your R function, the function that you want to find a root for, and you want to apply Newton's method to that. So the Newton system of equations, in the case of linear programming, corresponds to that system of equations. Okay? That system of equations. Now, there is something about the central path equations and the Newton system of equations in the case of linear programming that we can actually go a little bit farther and we can connect it with the barrier problem. And this is a nice way that we can more clearly see the difference between primal, dual, and barrier problems. If you think about the tweak complementarity conditions, right? If you think about that system of equations, or those equations can equivalently be written as we can in some way eliminate one of the variables. Let's say solve for s in terms of x, or the other way around, solve for x in terms of s. It's just move things from one side to the other. And then we can eliminate either s or x from this system of equations. So in particular, if you think about, say, the primal problem, then the primal central path equations will be the first system of equations. That is the equations you get if you eliminate s. Okay, so you don't explicitly deal with s as a separate variable, but you think about s as tau x inverse 1. So then you get that the primal central path equations are the first system of equations. Or if you eliminate x, then the dual central path equations are those equations there. So the first system of equations is essentially the optimality conditions for the primal barrier problem. The second one is the system of the optimality conditions for the dual barrier problem. Maybe I should write that down just so that it makes this be more precise. So the equations, so this is a little observation here. If you think about let's say the primal problem. Okay, the primal problem, it turns out that the KKT conditions are exactly that first block of equations there. So if you play with this, you get that the KKT conditions can be rewritten as A transpose Y minus tau X inverse 1 equal to C. And how do you get this? Well, actually plus here. Observe that C minus tau X inverse 1 is the gradient of the objective, right? And A transpose Y is just a combination of the gradient of the constraints. So the KKT conditions for this problem you can write like that, and of course AX equal to B. Okay, so that is a purely primal, if you want, a purely primal point of view. You could also do the same thing for the dual problem. Okay? You could also do the same thing for the dual problem. That is, take the dual problem, right? B transpose S, and then add, I guess if I were to work on the dual problem, I would do it this way, add tau, sum of the log of Si, where A transpose Y plus S is equal to C. Okay? And again, the KKT conditions for the dual problem, so for the dual problem, just the dual, without looking at the primal in any way, are, well, same thing as, so we have those constraints, but then we also have, we must have the connection between we must have also the connection between the gradient of the objective and the constraints. Okay? The gradient of the objective and the constraints. And it turns out that if you play with this a little bit, you get, so the grade, you would get something like this, B, for the objective, B minus tau S inverse 1. C. Oh, sorry, no, not that. You get this. B and minus tau S inverse 1 should be equal to some A and identity times some multipliers for the equality constraints. So let me put them V here. And then the V can be written in terms of this guy. So at the end, this is equivalent to what I have written there, and that is, so we have that, and of course the optimal, the feasibility. So if you play with this, essentially you can replace V in terms of S inverse 1. Okay, so then you get that, you can rewrite the equations as I have them there. A S inverse 1 equal to B, and A plus S equal to C. So the dual ones are a little less straightforward. The primal ones are very straightforward. If you look at that primal problem, you get that. But then this is an important distinction. If you look at the problem purely from the primal point of view, right? From the primal point of view, that is that system of equations, and then set up the Newton equations, you get these equations. Okay? If you look at the dual problem, you get these equations. Now, if you look at the Primal-dual problem, we get, let's see, I managed to displace the Primal-dual problem, we get these equations. Okay, so these are the primal, so these are the Primal-dual equations. These are the purely primal, and these are the purely dual equations. It turns out, and this is a very, very key aspect of Primal-dual algorithms, the Primal-dual equations make the step here, delta x, delta y, and delta s. They make them depend on the previous x, y, s. So the primal and dual variables are very, very interdependent. If you look only at the, say, primal barrier method, that traces everything purely in terms of the primal variables. the dual variables play no role. So this is a key difference between the Primaldual method and the barrier method. The Newton step that you compute in the Primaldual method, again, depends very much on where your previous primal and dual points are. It relates them. And somehow what that means is that the algorithm takes more advantage of duality, or takes duality, exploits duality, relies on duality, and uses duality in a much more effective fashion than if we just look at a purely primal, a purely dual method. If you think about what happens here, in the Primaldual Newton system of equations, both big S and big X, both of them show up. If you look at the purely primal Newton system here, only X shows up. If you look at the purely dual, only S shows up. Somehow they both come up here, and in some way the algorithm is able to harness information from both of them. So in that regard, that is a key difference between the Primaldual and the purely primal or the purely dual barrier method. Okay, so that's with regard to the Newton system of equations. So let me flash some examples that I just took directly from the book of Boyd and Underwood. So these are some examples of how the barrier method compares to the barrier method, the primal barrier method, how that compares to the Primaldual method. So here, mu is equal to 10. Remember, mu is like 1/sigma. So the sigma in our algorithm that we described earlier is 110. So this is the same picture that we showed a little earlier a week ago. This is how the duality gap looks like in terms of number of iterations. And here is how the Primaldual surrogate duality gap looks like. So the surrogate gap goes to 0 faster, but it's only a surrogate gap, right? It's not a real gap. But then here we also see what happens to the primal and dual feasibility. Okay? So the primal and dual feasibility, initially the iterates are not feasible, but at some point there is kind of a phase transition and we essentially achieve feasibility. Okay? So after a certain number of iterations of the order of, say, 25 or so, we essentially have solved the problem to very high accuracy via a Primaldual algorithm. Okay? By contrast, in the purely barrier method, it takes more time to get that level of accuracy. One more thing to test your understanding or challenge you since you're here. Does anyone have a clue of what this has to do with? Why would we observe that kind of very, very sharp kind of phase transition? Like the residuals, the norm of the residuals is getting smaller and smaller, and all of a sudden, at a particular point, it jumps just to 0 essentially. So it's like at some point something magical happens to the line search that gets us in one single iteration to perfect feasibility. What could have possibly happened at that point? Think about what could be so special about this step length that would get us from something that is not feasible to something that is feasible. As far as these are linear programs, right? These are just the primal and dual. In this case, the primal and dual constraints are linear, right? In this case, the residuals. Yeah, here. I guess I didn't have to remove this. In this case, these guys are linear, right? In this case, this would be the dual residual, and this guy here would be the primal residual. So okay, let me leave that as a constraints so that, you know, maybe someone can think about that. If you're curious, come back on Wednesday and I'll tell you what happened there. Because I want to use the last few minutes for something else that I think is pretty cool. Something similar happens here in terms of the total number of, say, iterations to either just reduce the duality gap in the barrier method or get a very accurate solution in the Primal-dual method. Essentially, the punchline is that the Primal-dual method is much more efficient. But I want to use the last few minutes today to discuss an extension to semi-definite programming. It turns out that the same kind of machinery that works so well for linear programming, a lot of that also works well for semi-definite programming. So here is semi-definite programming and the dual. Okay? Semi-definite programming and its dual. So observe that there is a similar kind of format to how linear programming and the dual, right? Here we have variables that are matrices. And this, just to refresh your memory, the dot product here is the trace inner product. Okay? And one important thing, this is something I was discussing at the end of our last class. These are special cases of conic programs. The duality doesn't always hold, but it holds if we have some kind of nice Slater condition. So provided that we have Slater conditions for both the primal and the dual, that is, if we have strictly feasible solutions for the primal and the dual, then everything works very nicely. We have strong duality, both the primal and the dual are attained. We don't have any pathologies. And something nice about the Slater condition is that also it's perfectly compatible with interior point methods. Okay? So let me rewrite again the primal and dual problems here. And I'm abbreviating all of these equations, all of these conditions here, all of the constraints here as simply A of x equal to B. I use fancy A so that it indicates the vector that has all these components. So it's A, this script A is a linear map from symmetric matrices to Rn. And then we have something that looks almost identical to the optimality conditions for linear programming. That is, we have a solution to the primal and dual semi-definite programs, if and only if we have primal and dual feasibility, and we have complementarity. So compare that to this. That looks very similar to this. Except that now we are talking about semi-definite. Now, so let me put this back here. If you look now at the, if we were to use interior point methods, one way of essentially extending everything that we have discussed so far to semi-definite programming would be to replace, so this is the complicated constraint, this constraint here. Oh, there's a typo in my slides. I just noticed that, and I apologize. It should be S, of course. So this is S. Not C, but of course it's S. So sorry about that. This is a big typo. This has to be an S here. It's not C, that is the variable, but S. So we have the primal and dual problems. These are the optimality conditions for the actual problems. If we then replace the constraints here, the difficult constraints, the positive semi-definite constraint, if we replace it with a suitable barrier function, the barrier function for the semi-definite column is log determinant. If we replace it with that, then we have a primal barrier problem, a dual barrier problem, and then the optimality conditions for both is like this. So you see how this kind of very, very cool analogy to what happened in the linear programming case? So think about the correspondence between these equations and these equations. That is very, very analogous to what happened before in linear programming between these equations and these equations. It's a very similar kind of analogy. Now, we can also play the same game of eliminating one of the variables in terms of the others, right? So if you think about this, we can eliminate x in terms of, we can write x in terms of s, or the other way around. And then we have essentially primal central path equations. The primal central path equations would be that system of equations there. If we apply Newton's method to that system of equations, we get these equations. This gets a little bit more technically involved because we are linearizing the first system of equations. The variables are matrices, right? And it's the inverse of a matrix. And we need to linearize the operation of taking an inverse of a matrix. So think about that as the nonlinear map from matrices to matrices, that is, take the inverse. And we want the Jacobian of that map. So it's a little bit of a complicated problem, but it turns out that the linearization, so the Jacobian of x inverse, is this operator that multiplies left and right by the inverse. So the first system of equations is linearized like this. So these would be the Newton equations if you are solving the problem, say, from a primal perspective. And then you have similar Newton equations if you are solving the problem from a dual perspective. Okay, so those would be the primal and dual. So here's the equations, right? And what we have done there is eliminate, say, S, and then you write the corresponding equations. So this would be the primal Newton step, and we have similar dual Newton steps. If you were to naively take this, right, and linearize it, okay, the central path equations, maybe I should have written everything on the left. So tau I here, all of that equals to 0. If I try to linearize that system of equations, the Newton step, if I were to look at some kind of primal dual Newton step, the Newton step would be this step. So this is for, this would be, this would look very natural. But then there is something that, some particular technicality that comes up in semi-definite programming, and it's that if we solve this system of equations, x, s are matrices, and I want delta x and delta s to be new matrices that I add up to x and s. It turns out that something, this is very, this is a little bit technical, but something that happens here is that even if s and x are symmetric positive definite matrices, this is something that you learn in your freshman or sophomore linear algebra course. If you take the product of two symmetric matrices, is the product symmetric? Yes or no? The answer is not necessarily. So, unfortunately, the variables that we deal with here are symmetric matrices. When we make this product, there is no reason to expect that product to be necessarily a symmetric matrix. And it turns out that if you just try to solve this, these guys are not necessarily symmetric. So we kind of get in a conundrum here. We run into some difficulty here because we do not preserve the symmetry of the matrix. So the appropriate primal dual Newton step that does work has to be more complicated than that. Essentially, we have to linearize. So here in the central path equations, we have to linearize this guy. Linearize this in a way that preserves symmetry. So we can do it in some purely primal fashion. That's what I described earlier, or a purely dual fashion. That's this. If we want to do it in a primal dual fashion, then that is done via something that these two gentlemen, Nesterov and Todd, developed in a very highly cited paper from about 20 years ago. They call it the Nesterov-Todd direction. You try to linearize, again, the idea is to linearize this system of equations here. So you linearize it with some kind of matrix W, where the W is some sort of geometric mean of x and s. And when you do that, if you do that, then you have a primal dual algorithm for semi-definite programming. But it's of course much more complicated because now the Newton equation that was so simple in the linear programming case, and it was so simple in the previous version of the Primaldual method that I described in the first half of the class. If you want to extend that to semi-definite programming, then you have to mess around with this nested of path direction. It's much more involved. Except for that detail, the rest of the machinery of Primaldual and pure methods also extends to semi-definite programming, and you get a nice algorithm that also solves semi-definite programming problems. So the main, if you want, template of the algorithm is very similar to the ones that we saw earlier. But then the part of the algorithm that gets much more complicated is the Newton direction. The Newton direction now becomes this nested of path direction. So my time is up for today. That's all I wanted to tell you about Primaldual and pure methods. Here are some references. So these two, this is very standard for linear programming. This is a very famous paper by these two guys. They developed this machinery of semi-definite programming. And of course, the book of Boyd and Vandenberg, they developed it. They have a nice exposition of Primaldual and pure methods. So with that, let's stop for today.